So in this video I'm going to talk to you about Vsepr theory, or valence share electron pair repulsion theory. So the big idea of this theory helps us understand why we draw certain molecules in certain shapes rather than just any old shape, and we'll use a couple of examples to go through that. So the big idea of this video is really explaining how you have electrons that repel each other all around a nucleus of an atom in a molecule. Those electrons exist in orbitals which have a particular shape, and they can vary on how close to the nucleus they are. So how do they actually arrange inside a molecule? And really we're talking about the shape of molecules. So how do you take all these negatively charged electrons whizzing around an atom, take them and then arrange them in a certain shape so a molecule has actually stays together rather than just all the electrons flying apart? So how does this all these electrons arrange themselves around an atom? And there's a very particular way that we believe that happens. So before we go any further, I just want to show you kind of a way to represent molecules in 3D. So this is a good example of methane. So if you try and draw this in class, we can just draw 4 straight lines, which we've been doing, which has been okay for a little while, but there's actually a better way. And actually if you look, there's 4 bonds on this molecule. 2 of them are in the same plane, and then one of them is coming out towards the camera, then one of them is coming straight back. So the way that we show that, and the way that we'll be using in class, is this way. So we use straight lines to represent the 2 bonds that are in the plane of the paper, or in the board in this case. So then the bond that's coming out towards us, or towards the camera, we're going to represent with a thick wedge. And then the bond that's going back into the board we represent with a dotted line. So whenever you have a shape that isn't completely in 2D, so in one plane, we represent them this way. And we'll use a lot more examples of that. And actually the models really help see that when we're working with shapes and so on. So that's what we'll be using from now on. Okay, so we're learning about Vsepr theory, we're learning about particular molecule shapes and how that comes about and why that happens. So I'm going to use an example. We're going to use ammonia to talk about why particular pairs of electrons have different amounts of repulsion. So if we look at ammonia, we're going to look at the energy level diagram quickly. So we're just going to deal with nitrogen in this molecule rather than hydrogen as well. So there's the 1s. Then we go up to the 2s, showing the electrons in different spins. The 2p orbital has 2, 4, 6, 7. So this is the arrangement of nitrogen, which has a total of 7 electrons. So we show the orbital the electron promotion. So that electron would go up there to the 2p, and then this orbital would increase in energy. This one would drop slightly in energy. So then what we'd end up with, I'm taking a shortcut here, which I hope you're okay with. So we end up with 4 orbitals that all have the same amount of energy. First one has 2 electrons, and then the next 3 all have 1, spinning the same direction. So another way of saying this is that we've created 3 sites for bonding. So there's 1, 2, 3 areas that these 3 hydrogen atoms can share electrons with. So that's where we get the sp3 shape from. So if we're going to draw out ammonia, we have a nitrogen atom in the middle. So we have a pair of electrons that's not bonded to anything. That was a lone pair. And then we have 3 more sp3 hybrid orbitals. These are all supposed to be the same size and shape. Then these 3 would overlap with each of the hydrogen. So that's how we end up with ammonia. So the reason or the cause for Vsepr theory, and really that's all about how electron pairs repel each other, because remember they've all got the same negative charge. So these electron pairs that are in this orbital, so you've got two electrons, so one from the hydrogen and then one from the nitrogen existing in this area, kind of this overlap of orbitals. So that pair of electrons is experiencing attraction from both the hydrogen nucleus and the nitrogen nucleus. Admittedly though, it's being pulled more towards the nitrogen because nitrogen is more electronegative. But that pair of electrons is being pulled in between those two. So because of that, it actually has less energy, slightly less energy, so it takes up less room. So that's true for that pair of electrons and then these two pairs right here. So we'd actually call these bonded pairs of electrons because they're bonded between, or they're being shared between two atoms. I don't think I've said this yet, but Vsepr theory is all related to covalent molecules. So we're not really dealing with metals and non-metals, just non-metals bonded to each other. So we have three bonded pairs of electrons being shared covalently, and then we've got this lone pair of electrons right here. So because this lone pair isn't experiencing the attraction between two nuclei, in this case it's just one, this can actually take up more room. So imagine these electrons have slightly more room to maneuver compared to this pair or these two pairs, so these are all the same. So the cause for electron pairs repelling each other differently is caused by bonded pairs, for example, being attracted by two nuclei, lone pairs just one. So that's the cause of Vsepr theory. It's all to do with how the electrons are being attracted to different nuclei. So that's the cause of Vsepr theory. Another thing to say here is that the attraction between bonded pairs is slightly less because they take up less room. The attraction between lone pair and bonded pair is actually more repulsion. So this lone pair is pushing down on these two lone pairs with more force than these two are pushing away from each other. And we'll look at water molecule in a second, and that has the oxygen has two lone pairs, so that shape is different again. Yeah, I'm going to erase this and then move on. So the next thing to do is to look at H2O and then talk about molecular shapes. But before I do that, I'm going to go back to methane, which is represented with this this structure. So we've got 4 carbon-hydrogen bonds, CH4. So when we're talking about shapes, we compare a lot of things to this particular shape that carbon makes when it bonds. Carbon usually makes the same shape, even though there's different things bonded to it. In a lot of cases, not all cases. So we call that shape, so I'll draw methane again, using this method. So this is the bond going back into the board, this one's coming out towards you. So this is called a tetrahedral. So these are 4 equal bonds. These are all bonded pairs, so they're all repelling each other equally. So the maximum distance that these bonded pairs can have from each other and still stay in the molecule is 109.5 degrees. So the tetrahedral shape is this 4 equal bonds, 0 lone pairs, and then the big thing here is these electron pairs all repelling each other. These are all the same angle from each other, so all 109.5. So we'll be using the term bond angle, and that's what we mean. So this is 109.5, as is every other bond between each other. And it's a lot easier to see with the models, which we'll be spending quite a bit of time with. So the ammonia excuse me, we'll talk about ammonia again in a second, but that was the idea of shape, molecules having a particular shape. So shape influences polarity, and polarity also influences shape. It actually depends on the molecule to some degree, but let's use an example that we've talked about in class. So we're going to look at H2O. So one way to draw the water molecule is this way. So we've got 2 lone pairs of electrons that aren't bonded to anything, and then we've got these 2 bonded pairs. So that would be one way. the other way would be like this. So the lone pairs are together this time, and the bonded pairs are together. So there's a reason why we don't use this particular shape, and it's because of polarity. We know that water is a polar molecule, it's cohesive and adhesive. So water molecules stick to each other. So what you're probably screaming at the video camera, the TV right now, is that there's no dipole, and you'd be absolutely right. So if we looked at the electronegativity values and subtracted those and labeled delta negative charges, here you don't have a dipole. So we know that it has to be incorrect because water is so cohesive and adhesive. So there must be a dipole. So this has to be the shape. So this one is completely wrong. And we've been drawing water in this shape, and this is why. So there has to be a dipole based on the physical and chemical properties of water. We've used polarity to kind of help explain that as well. And we can use Vsepr theory to talk about the shape. So, because you've got two lone pairs of electrons, that's the strongest amount of repulsion you can get between pairs of electrons. So it goes lone pair, then the next is lone pair and a bonded pair. So this would be the strongest, this would be next, and then these two, the two bonded pairs, would be the weakest. So this shape has to come together so that the lone pairs of electrons can take up as much space as they need, because those electrons are moving with a lot more, they're taking up a lot more space than the bonded pairs. So this is how the water molecule comes together. The lone pairs go next to each other, and the bonded pairs kind of come next to each other to maximize the amount of space that all these different electron pairs need. So this has a really imaginative name for the shape. It's actually called a bent shape because of the bent shape. But the bond angle is slightly less than that tetrahedral. So remember, this is the tetrahedral shape. So those bond angles in between two of the white spheres would be 109.5. And that's because you've got 0 lone pairs and all bonded pairs. So they're all repelling each other equally. However, in the case of water, you've got two bonded pairs repelling each other less than these lone pairs are repelling everything else. So they're repelling each other as much as they can, and then pushing down this V shape to make it actually less than a tetrahedral would be. It's kind of similar to a tetrahedral shape because you've got 1, 2, 3, 4 pairs of electrons, but the lone pairs makes all the difference, and that they repel each other more than the bonded pairs do. Okay, so if you look at ammonia, which has that lone pair, this has a slightly different shape because there are less lone pairs and more bonded pairs. So the bond angle is actually a little bit bigger than this, but still less than a tetrahedral because it's got that lone pair. So the bond angle here would be 107 degrees. So it's kind of in between water, which has more lone pairs, so repelling each other more, making the bonded pairs have a smaller angle together. And then on the other side, you've got methane, or tetrahedral shape, that has just bonded pairs repelling each other equally. So it's the lone pairs that really have a big effect on the shape. Well, actually, the repulsion of lone pairs. Okay. So the last thing to say, we'll do a lot more work with shapes and then identifying the shapes. There's some notes that I'll provide that help explain it a little bit further. But really what we're going to do now is look at electron areas. So the tricky thing with electron areas is that they don't really include double or triple bonds. And I'll show some examples in a second. So for H2O, what you do is you count up the number of electron areas. So this would be 1, 2, 3, 4. So then the next thing to say is that we've got 2 lone pairs, 2 bonded pairs. 2 bonded pairs. So 1, 2, 3, 4. 4 areas where there are electrons are. It's a really clever name, electron areas. So 2 lone pairs, 2 bonded pairs. In the case of ammonia, we've still got 4 electron areas, but we've got 3 bonded pairs and one lone. So the big thing here is the number of lone pairs and bonded pairs. The ratio really has a big effect on the molecule's shape. And then also shape influences polarity. So if there's no dipole, if the shape makes it so there's no dipole, it doesn't matter how electronegatively different the atoms are, the molecule won't be polar. So I'll show another example of that in a second. So that's how we tell the number of electron areas, which is actually really important when we look at shape. Methane that we've looked at right there a couple of times now. So that has 4 electron areas. So carbon makes 4 bonds, 1, 2, 3, 4. So 4 electron areas, 0 lone pairs. And that actually would be a tetrahedral shape. And it is a tetrahedral shape. And then the last one would be an example with double bonds, so that would be CO2. So carbon, whoops. So what you notice in here is that oxygen has got 2 lone pairs, but when we talk about Vsepr theory and electron areas, we only use the central atom. Really important note. So we don't care too much about what it's bonded to, just the atom that's in the middle, the one that's got the most things bonded to it. And the quick way to look is that usually when you write the formula, the atom, the first atom, or the first element rather, is the one that's got the most things bonded to it, usually. Not in the case of H2O. Alright, so this has got, so that was for this methane. So for CO2, we just count this as 1 electron area. So 1, 1, so that's 2 electron areas, 0 lone pairs, and then 4 bonded. And then if you look at the shape, this really is kind of symmetrical, so this would just be linear, and this would be 180 degrees. So the shape of this molecule influences its polarity, because even though these are polar bonds, the molecule itself is non-polar because it doesn't have a dipole. So that's the big idea of Vsepr theory. We're looking at how electron pairs repel each other. That difference is caused by in between 2 atoms that are sharing electrons, like a covalent bond. Those electrons move, take up less space compared to a lone pair. And then lone pairs repel each other quite a lot, so the more lone pairs you have in a molecule around the central atom, then that really has the biggest influence on shape. All the different shapes have names, which we'll go over in class. The big thing is learning how to count electron areas, which we just went through. And that's Vsepr theory.